Hello, ladies and gentlemen, and welcome to our virtual classroom. Today we are going to be going over triangles. And what I want to do today is simply review things that you may, or rather should have covered in 5th grade before we get into anything new regarding triangles. And so let's begin with the actual word triangle. In fact, when you see the word triangle, the prefix tri literally means 3, and angle obviously means an angle, right? So a triangle is a shape with 3 angles, right? And so obviously we're looking at shapes that look like this, or maybe like this, or maybe like this. As long as it has 3 angles, or rather you might also see it as a 3-sided figure, that is a triangle. In fact, a triangle is the simplest polygon, and we'll talk more about polygon later, but it's the simplest two-dimensional shape, if you will, that we're going to be talking about. It's the one with the fewest amount of sides. You need at least 3 sides. So there are 2 ways of classifying triangles, ladies and gentlemen. And again, this should be a review. Hopefully this is a review. We're classifying by the sides, ladies and gentlemen. You are going to have either a scalene triangle, an isosceles triangle, or an equilateral triangle. And as far as these notes, feel free to pause at any point, especially if you're writing these down, so that if I'm going too fast, you can rewind and listen to it again, maybe as you've already written it down. So again, I encourage you to pause and rewind as you see fit. But like I said, we have 3 different types of triangles if we're looking at the sides of the triangle. So in a scalene triangle, scalene literally means that all the sides are different. All the sides are different. That would be a scalene triangle. And if all the sides are different, we can assume that all the angles will be different too. So if you're given a triangle and you're given all the different angle measurements, and you see that they're all different, then you can assume that all the sides are different too. So it would be a scalene triangle. Very similar to these examples that I've posted here on Schoology. If you look at the notes on Schoology, notice the scalene triangles. Here, I am not giving you the measures of the sides, but rather the angles, how open they are. And notice that here on the scalene triangles, all of these are scalene triangles, the angle measurements are always different. They're all different to one another. And so given that, ladies and gentlemen, that means that all of the sides are going to be different from one another. All the sides, so this side will be different than this side, which will be different than this side. And this one down here, this side is different than this side, which is different than this bottom side. Excuse me. So these are all examples of scalene triangles. Remember, we're looking at the sides. Moving on, ladies and gentlemen, we have the isosceles triangle. Isosceles triangle, and notice the ways that it's spelled. And an isosceles triangle is one, again, looking at the sides, where it will have 2 equal sides. 2 of the sides will be equal. 2 of the sides will be the exact same length. And again, we can assume that if 2 of the sides are equal, then 2 of the angles will be equal as well. And a good way to remember an isosceles triangle is I. How many eyes do we typically have? We have 2 eyes, right? So isosceles triangle, 2 eyes. So 2 of the sides are exactly the same. That is an isosceles triangle. Again, looking at our examples from Schoology, notice that the isosceles triangles, ladies and gentlemen, will be 2 of the angles will be the same, making 2 of the sides to be the same. So in this example right here, we can see that this side and this side are exactly the same, just as the 2 opposite angles are the same. That is an isosceles triangle. If we look at this triangle right here, this side and this side are exactly the same, just as this angle and this angle are exactly the same. Again, an isosceles triangle. Looking over here, we can see that this side and this side are the same. How do I know that that's true? Because this angle is 75 degrees and this angle is 75 degrees. Again, an isosceles triangle. 2 of the sides are the same, so 2 of the angles will be the same as well. And finally, we have an equilateral, or some people say equilateral or equilateral triangle. And you can see the prefix equi or equi means equal, and lateral means side. So equal sides. That means that all the sides of this triangle, ladies and gentlemen, all the sides are equal. So all three sides will be the same. And if all three sides are the same, then all of the angles will be the same as well. So again, if we look at some examples of equilateral triangles, notice that no matter how large or how small the triangle is, the angles, how open each of the corners is always exactly the same, and it will always be 60 degrees. So again, it doesn't matter how big or small, it is always open to 60 degrees. It is always open to 60 degrees. And that will always be the case in an equilateral triangle. All right, and that's part of our definition in an equilateral triangle. You can also call it an equal angular. Again, equal, the same, angular, we're talking about the angles. All the angles are the same, so all the angles will measure 60 degrees. So again, if I was going a little fast, I recommend you rewind and rewatch that and see if hearing it a second time will make a little bit more sense. So again, this was classifying triangles by their sides. So ladies and gentlemen, what if we're talking specifically about the angles? What if we were going to classify these triangles by their angles? Well, we have, let's begin with the acute, obtuse, and right triangles. And just as a quick reminder, ladies and gentlemen, there's three types of angles. There's the acute angle, which an acute angle is an angle that measures less than 90 degrees. An obtuse angle measures more than 90 degrees, and a right angle measures exactly 90 degrees. So an acute angle, not a triangle, but if we're looking at an angle, 90 degrees, ladies and gentlemen, is like the corner of a square or rectangle. So if I were to draw a square or rectangle like I've done here, 90 degrees will be the measurement of how open this angle is. So this angle right here will be a 90-degree angle because this is open exactly 90 degrees. And notice that it doesn't matter how big or small. Let's say if I draw a smaller rectangle right inside of it, notice that it's still open the exact same amount. That is still 90 degrees. So it matters not how big or small the shape is, it's how open. Think of it as a door, okay? If you have a very large door and a very small door, notice how here in these two examples, just because it's a larger door, it still has a very small angle right here. Whereas this smaller door is open a lot more because, again, angles have nothing to do with how long the arms are. It's all about how open it is. All right, so if it's barely open, it is a small angle. It is an acute angle. And then if it's open a lot more, then it's obviously a larger angle. So with that in mind, ladies and gentlemen, an acute triangle is a triangle where all the angles are less than 90. All the angles are smaller than this degree of openness. This would be a 90-degree angle right here. So in an acute triangle, all the angles are less open than this much. And in fact, for an example of an acute triangle, ladies and gentlemen, again, we can go back to our notes on Schoology and notice that here we have examples of acute triangles. Notice that if I were to try to put a rectangle right inside each of these angles, notice that it is open way less than 90-degree angles, than a 90-degree angle. 90 degrees would be from here to here, so this is open less than 90 degrees. Again, if I were to put a rectangle right here, again, it's less than 90. One right here, again, it's less than that. It's more closed than 90 degrees. That is true of all the angles that we see here in an acute triangle. Again, an acute triangle is where all the angles, each of the angles is less than 90 degrees, less than the corner of a rectangle. All right, that is an acute triangle. You think of a cute little triangle, okay? It's not that it's a small triangle, but the angles are smaller than 90 degrees. Then we have an obtuse triangle. Obtuse means that only one of the angles is more than 90 degrees. One of the angles is open more than the measure of the corner of a rectangle, okay? So if we can see our examples over here, again in the notes, notice the obtuse triangles, and here's a good example. Notice that these two angles are really small, But then look at this angle right here. Notice how much it's opening. It's definitely opening more than the corner of a rectangle. You see? In a rectangle, it would be exactly from here to here. But the triangle here is opening all of this. So that's why this would be known as an obtuse triangle, because it has one angle that is open really wide. Same thing up here. We can see that these two angles are really small, but then we have this really wide, really open angle. That's an obtuse angle, so this would be an obtuse triangle. Over here in E, again, we have an obtuse angle right here, so that would be an obtuse triangle. And then finally, ladies and gentlemen, we have right triangles. And in a right triangle, ladies and gentlemen, as we can see down here, we see one right angle, one angle that is exactly 90 degrees, one angle that looks like if it were the corner of a square or rectangle, as we see over here. And they will oftentimes put a little square right next to the angle to show you that that is a right angle, so you can assume that that is a right triangle. Now, the other two angles will be smaller than 90 degrees, but it has one right angle. We see that right angle right here, and right here. Once again, ladies and gentlemen, if I was going too fast, I recommend you rewind to hear that again. Maybe the second time around, it will make more sense. Anyways, ladies and gentlemen, we're going to cover this in more detail next time. But for now, I do want you to keep in mind that if you were to add up all the angles inside a triangle, if you were to add up all three angles, regardless of the triangle, the sum, the addition of all three angles will always add up to 180 degrees. That is a rule. You cannot make and you cannot find a triangle where if you measure the exact measurements of each angle, of how open each angle is, where it will not measure 180. It will always measure 180 degrees. All right. And so even over here, when we see the actual measurements of these angles, as we see here in our triangles given, if you add 135 plus 30 plus 15, that equals 180. Over here, 40 plus 120 plus 20, again, that equals 180. Over here, we have a right triangle. Notice there's a 90-degree angle. 90 plus 20, that's 110 plus 70, that's 180. So it doesn't matter which triangle you take. Equilateral triangle, 60 plus 60 plus 60, again, that is 180. It does not matter, ladies and gentlemen. It will always measure 180. And we will cover that in more detail next time. Finally, ladies and gentlemen, there is one new thing that I do want to show you, and that is known as the triangle inequality property. This is a property, a rule that is true of all triangles, the triangle inequality property. And here's the dictionary definition. But what I want you to focus on, and you can write that down. I do want you to write it down. I want you to be aware of it. The sum of any two sides of a triangle must be greater than the length of the third side. But I really want you to pay attention to this right here. I'm going to go slower. The triangle inequality property basically tells us that if you were to add up the sum, if you were to add up the two shorter sides on a triangle, whatever you get from adding the two shorter sides must be more than the longest side. So again, if for any triangle, if you take the two shorter sides and you add them up, that must be more than the measure of, yes, that must be more than the measure of the longest side. For example, let's suppose that you have a triangle. If we look at this second example right here, we see that one of the sides is supposed to be 3, the other side is supposed to be 3, and the other side is supposed to be 7. Well, ladies and gentlemen, the question is, can you even make a triangle with these 3 sides? All right, remember, the sum, if you add up the two shorter sides, what you get must be more than the longest side. Well, right here we see that 3 plus 3 is equal to 6. Is 6 more than 7? No, it is not. 6 is not more than 7. So guys, it's actually impossible to make a triangle with those 3 sides. All right, that would be impossible. It would be like trying to make a triangle, as you can see here, with these pens and, let me see, what else do I have here? With these pens and this ruler. You might think, well, Mr. Lugo, you have 3 sides. Can't you make a triangle? Well, let me try. And you have to put them end to end. So when I try to put them together, notice that the two shorter sides are not even long enough to meet. They're not even long enough. So you cannot make a triangle unless the two shorter sides together are more than the longest side. Kind of like what you see in this other example. Let's suppose that I have these three. Notice that the two shorter ones, which are these two, together are longer than the longest one. So now I can make a triangle. So again, the two shorter sides must together be longer than the longest one. All right, like you see here in this example down here. We have the two shorter sides, 4 plus 4, that's 8. 8 together is more than the longest side, which is 7. So yes, you can make a triangle. And obviously, if all the sides are the same, that's an equilateral triangle. Yes, you can make a triangle. All right, ladies and gentlemen, I hope this video was helpful. I don't want to make it much longer. I know there was a lot of notes in this one, but again, I hope this was helpful. And with that in mind, I will see you next time.